equilibrium, you could tell which acid was more soluble based on the K value, right? The greater the K value, the more soluble the acid, the greater the dissociation of the acid. You cannot do that for ionic solids, okay? And the reason you cannot do that for ionic solids is because they dissociate in a different number of particles. So it's not just like an acid will only lose one proton at a time, so the acid dissociation equilibrium was always x squared over whatever your initial concentration was. There will be coefficients, there will be powers in these equilibrium expressions. So you can't just look at the KSP to determine which salt is more soluble unless the salts dissociate into the same number of particles. So if the salts break down or have the same I, remember? I is the number of particles they dissociate into. If they have the same I, then you can just look at the KSP. But if they don't have the same I, you actually must calculate the solubility, okay? So relative solubility cannot be measured or determined by simply comparing KSP values. You must also take into account the composition of the salt. And when I say composition, I really mean the I value. So, if they ask me, like they do in sample problem number 5, which salt is most soluble, the first thing I want to do is figure out how many particles they dissociate into. So in silver chloride, what's the I? 2. Right. This dissociates into 2 particles.
So the I is that like Van Hoff?
Yep. The I is the Van 't Hoff factor. It's the number of ions that are generated when the salt dissolves in water for every mole of the salt. Okay? All right, silver chromate here. Anybody know what the I is? 3. Good. 2 silvers and 1 chromate. And how about silver phosphate? 4. Uh-oh. Since the I is different, we got to calculate X to figure out who's most soluble. And let's make a note of that. Since the I is not the same, we must calculate X. I lost part of my screen here. I don't know where it went. It's off the screen. God bless you. I's were the same, then we could just look at the largest KSP being the most soluble. You could save yourself a lot of work, okay? But it's not. So we have to calculate the solubility for each of these salts. So let's do it. The first one, AgCl. We write our reaction. It's the dissociation of the solid into Ag plus. CO minus. We put some of this in water, and it's, even though we consider it insoluble, a little tiny bit of it's going to dissolve. That little tiny bit is our solubility, and that's what we're trying to find. So our KSP equals our concentration of silver ions times our concentration of chloride ions. That's 1.5 times 10 to the negative 10th equals x squared. And so if you solve for your x, you should get for silver chloride 1.22 times 10 to the negative 5th. So that's your solubility of silver chloride. We're going to do the same thing with the 2 remaining salts. So please go ahead and calculate the solubility right now on your own of silver chromate and of silver phosphate. Okay? Thank you. All right, everybody, let's come back to this and check ourselves because we have to get an answer to the question. This is just what we needed to do in order to answer the question. So for silver chromate, I got the solubility to be 1.3 times 10 to the negative 4 molar. And for silver phosphate, I got the solubility to be 1.6 times 10 to the negative 5th molar. So there have been some questions about how you take the fourth root of something. There are multiple ways. One of the ways you could do is after you take 1.8 times 10 to the negative 18th and divide it by 27, you get like 6 times 10 to the negative 10th or something like that, right? 20th? Okay. You can take the fourth root of that. So in your math button, this one's out of batteries. If you go to the math button, there's a root. It's number 5, okay? Where you can go ahead and put in like the fourth root before where it says answer. Yeah, you can put a 4 there and then put your answer under the square root sign, okay? Or you can take your, what was it, 6 times 10 to the 20th or whatever it was it negative 20th? And raise it to the 1/4 power. That's something you also could do. You could raise it to the 0.25. It's up to you, however you choose to solve that. One of the more common mistakes is forgetting to cube the 3. Okay, that's one of the more common mistakes. 3 times 3 times 3 is 27, right? 9 times 3 is 27. X to the 4. Okay, so what's the answer? What's the answer? Right, the second one, B, is the answer. This is most soluble because it has the greatest solubility. Look at what they are. 1.22 times 10 to the negative 5, 1.3 times 10 to the negative 4, and 1.6 times 10 to the negative 5th. Therefore, Ag2, silver chromate, CrO4, is the most soluble. Remember, we would not have to go through all that math if they had the same I value. Okay, then you could just go with whoever has the largest KSP is the most soluble. And if you look here, you can even see that this one did not have the largest KSP. A had the biggest KSP. Okay, so you can't just look at KSP when they dissociate into different numbers of ions. Questions on that? Relative solubility. Okay. Uh-oh. That's not what I want. I want common ion effect. Let's find that. That's not next, right? Is common ion effect next?
Yeah.
I thought. Uh-oh. I don't think I have it. No? That was complex. Complex ion. Common ion. All right, that's okay. We'll wing it from here. Okay, this is Roman numeral 4 in your notes. I'd like to get through 4 and 5 if possible. I think we should be able to do it. We'll see. Maybe not. Maybe just 4. Anyway, Roman numeral 4 is called the common ion effect. And we saw this with acid dissociations. And basically, it's the same idea, is that now what we will be doing is not dissolving these insoluble salts in pure water, but we'll be dissolving them in water that has one of the ions already present in it. And what that will do is depress the dissociation of this insoluble salt and make it even smaller. Okay? So the presence of a common ion will shift the equilibrium to the first blank should be left. Insolubility equations. In other words, adding a common ion that doesn't react with other species in solution decreases the solubility of our already insoluble salt. Great, just what you wanted to hear, right? It's going to be a smaller number. All right, so let's show this. let's demonstrate this with the problems that we have. We are going to calculate the solubility of SRF2 with a KSP equal to 7.9 times 10 to the negative 10th in 3 different solutions. First, we're going to calculate it in pure water, and I think you can go ahead and start that. Second, we're going to calculate it in a 0.1 molar solution of strontium nitrate. So we're going to try to dissolve that in this. And then third, we're going to dissolve it in a 0.4 molar solution of sodium fluoride. Okay? But go ahead, let's start it in pure water first. Give everybody a chance to calculate it. Forgot to square the 2. Yeah. All right, compare your work with mine. I think most of you are there. You should have calculated your solubility of the strontium fluoride, right, to be 5.8 times 10 to the negative 4th molar in pure water. Okay? Yes? Any issues? Okay, so now let's calculate the solubility of strontium fluoride in a 0.1 molar solution of strontium nitrate. Okay? All nitrates are soluble. So what this really is existing as is 0.1 molar strontium and 0.2 molar nitrate. Okay? That's what it's really existing as. And so all of that changes in our dissociation of strontium fluoride is our, well, answer, and our I line. Because remember, when we put it in water, we're putting some of this solid in water, right? And it's going to dissociate into strontium ions and to fluoride ions. Well, if it's in water, there's no strontium and there's no fluoride. But if it's in strontium nitrate, there's some strontium there, right? How much strontium? 0.1 molar. There's the presence of a common ion. There's no fluoride, though. There's nitrate, too, but we don't really care about it, right? Because nitrate's a spectator ion. It doesn't have anything to do with the dissociation of our salts. So the presence of a common ion changes our I line. There's some strontium coming from the strontium nitrate. That's where the strontium's coming from. Okay? So this goes down by x, and this goes up by x, and this goes up by 2x. And so at equilibrium then, we have, some minus x of this, but we don't really care about that. We have 0.1 plus x of this, and we have 2x of this. And so our KSP, which is equal to 7.9 times 10 to the negative 10th, that's super small, right? So what we're going to do for anyone that we had an initial concentration of, we're going to assume the x to be negligible here. So we're going to say that this is about 0.1. So 7.9 times 10 to the negative 10 equals your concentration of strontium at equilibrium times your concentration of fluoride at equilibrium squared. So 7.9 times 10 to the negative 10 equals 0.1 times 2x squared. So 0.1 times 4x squared equals 7.9 times 10 to the negative 10th. And if we solve for our x, we should get, what'd you get, Christian?
0.00125.
No? Not 0.00125. Wait, maybe I have a mistake. I don't think I do, but I might. Hold on.
No, I know I did.
Yeah, I got that too. You forget to multiply it by 0.1?
No, I did it to cube, not squared.
Oh.
It's 4.4 times.
Good. And if we do our check, because we assumed x to be negligible, right? Our check is okay. Anybody have a problem with the math on that? Yeah, go ahead.
Oh, wait, I wasn't reading the question, sorry.
Okay. All right, so what you can see, everybody, if you look back to your solubility from A, right? Look at your solubility from A. Where did it go? 5.8 times 10 to the negative 4, and 4.4 times 10 to the negative 5th. The solubility's gone down of the strontium fluoride because, in essence, what you're doing compared to pure water is you're increasing the concentration of strontium ions. If you increase the concentration of strontium ions, the equilibrium shifts left, and so less strontium fluoride will dissociate, right? That's what we mean, the presence of a common ion to press us to dissociation, because it's like increasing one of their concentrations compared to pure water, compared to what they'd be in pure water. All right, we got one more. We got to do C. In letter C, we're doing this in 0.4 molar sodium fluoride, which all group 1 compounds are soluble. So that's really 0.4 molar sodium and 0.4 molar fluoride. But they want the solubility of SRF2. So that's still our reaction. SRF2 dissociating into SR plus 2 and 2F minus. Again, we're starting with some of this. The big difference, since we're not in pure water, is we're starting with one of our ions that we would dissociate into. Who are we starting with now? F. How much? 0.4. How come it's not 0.8? Yeah, the F that we're starting with isn't coming from the dissociation of SRF2. The F that we're starting with is coming from NAF, and there's only one F in NAF, right? So we're starting with, whoa, what happened there? 0.4 molar this, none of this. So this goes down by X, this goes up by X. This, though, will go up by 2X. because this change line is coming from the dissociation of the salt. Who cares about that? X, 0.4 plus 2x. K is still really small, right? So I'm going to assume the 2x to be negligible here. Okay? So this is going to be x, and this is going to be about 0.4. You're going to assume the 2x to be negligible. So KSP, which is 7.9 times 10 to the negative 10th, equals your x times 0.4 squared. Right? Your SR plus 2 times your F minus raised to its coefficient, which is a 2. .16, isn't it? 0.4 times 0.4 is 0.16 x. And if you solve for your x, you should get the 4.9 times 10 to the negative 9. Woo! And the check's okay. That looks like a 7, but it's really a 9.
Do you have to check?
Anytime you assume, you have to check. So I would take that answer and divide it by 0.4 and multiply by 100.
If you go on the exam, do they take points off?
Yes. Okay?
Yeah.
I know, it's tough.
How would you do B if it didn't check?
You could, well, you'd have to leave in what? What are we leaving in B? 0.1 minus 2x. So you'd do quadratic, right?
And coefficient is greater than 2.
I don't know, Penny. I don't know the answer to that. I don't know. You have to ask your math teacher. The bottom line is, it'll always check, or it should always check with these because the KSP is so small. Okay? So your x is always going to be a very small number. So I've never, ever had to use the quadratic with a KSP problem. It should, but you should show that you're doing the check, or you will lose points. Questions? I want to keep going. There's no calculations left. There's just content. So let's do section 5 and get it done. And then we're almost done with the whole chapter. We'll have one more day of it, at least. So section 5 deals with the same idea, but with pH and solubility. If they give you a pH, then you know you have an OH minus ion present, right? So if you look at pH can actually affect the solubility of many salts. And what I mean by that is this salt, magnesium hydroxide, which you really view that as a base, not really a salt. But there are other things that you would really view as a salt. It's generally considered insoluble. It's not one of our strong 6 bases. It has a KSP value. If you're in a basic pH, if the pH is basic, there's lots of OH minus ions present, right? And so what would you expect that to do to the solubility compared to in pure water? Decrease it. If you increase the concentration of someone, you'll shift away from what you increase. So if you have lots of OH minus ions, you actually increase the pH. Which will shift the equilibrium to the left and decrease the solubility of magnesium hydroxide. Okay, so those are the first 3 blanks under the equation. Okay? What if you're not in a base? What if you're dissolving this in a solution that has an acidic pH? Then what's floating around? Lots of H pluses, right? Uh-oh, what's that going to do? Decrease the pH. What are the H pluses going to react with in this dissociation reaction? OH minus, right? They're going to gobble up the OH minus ions, which is going to decrease the solubility of OH minus, or decrease the concentration of OH minus, which is going to shift this reaction the other way. It's It's going to shift that dissociation reaction to the right, which would increase the solubility. Okay? So addition of, in the second little paragraph there, addition of H plus ions decreases the pH and shifts the equilibrium to the right because because H plus bonds with OH minus, decreasing the OH minus concentration. Up and away, down and towards. So if you decrease the OH minus concentration, the reaction will shift to the right, which will increase MgOH2's solubility. So if they give you a salt and a pH, you should use the pH to calculate H plus and OH minus ions and use that as your eye line for whomever is, it's usually OH minus ions. So use that as your eye line for OH minus ions. There are other salts, though, that can be affected by pH, not just those that have OH minus ions. Flip your page. An example is silver phosphate. As you see, it says silver phosphate solubility is greater in an acidic solution than in pure water. Because if you think of this dissociation, 3Ag plus PO4 minus 3, PO4 minus 3 is a base, right? This is the conjugate base of HPO4 minus 2. This wants protons. If you're in an acid, it'll gobble up those protons. So in an acid, a reaction will occur where H plus reacts with that PO4 to produce HPO4 minus 2, and that's a reaction to completion. That's a really strong thing. So in an acid, what you're essentially doing in an acidic solution is decreasing the concentration of PO4 minus 3. The concentration of PO4 minus 3 decreases in an acid. Again, this is all relative to pure water. Okay? If you decrease the concentration of someone, you shift toward what you decrease. So this solubility reaction will shift to the right, increasing the solubility of silver phosphate. Okay? So it's all based on Le Chatelier's principle, how these are working. Okay? Now, not all salts will do this. Like if you look at the next thing, however, the solubility of AgCl is the same in pure water as it is in an acid. Can you figure out why? AgCl dissociates into Ag plus and Cl minus. This is the conjugate base of HCl, which is a strong acid. Does this want protons? No. Remember, if you're from someone strong, you have no acid-base properties. So I don't care if you're in an acid or not. This is not going to gobble up protons. So protons are not going to affect the solubility of that because Cl minus is not an effective base. It doesn't act as a base because it's from a strong acid. And if you're from someone strong, we don't care about you. So we don't care about the Cl- because it's not an effective base. So whether you're in an acid or you're in a base, doesn't matter for that reaction. Doesn't make a difference. Okay? Or you're in pure water. So the general rule is if your anion in the dissociation reaction is an effective base, meaning it's from a weak acid, if it comes from a weak acid, then your salt will show increased solubility in an acidic solution. But if it's not, like Cl- or NO3- or ClO4-, then it doesn't really matter if you're in pure water or you're in an acid, the solubility is going to be the same. So some other anions that can serve as effective bases, we could make a list 5 miles long. All right, maybe that's an exaggeration. But we see them all the time, right? F-, C2H3O2-. S-2. CrO4-2, CO3-2, SO3-2, SO4-2. Okay, the list goes on and on. We could really make a super long list, but etc. is good for today. Okay, if your anion is the conjugate base of a weak acid, its solubility will increase in an acid because this concentration will go down because it'll bond with the hydrogen ions. If you decrease the concentration, you shift that solubility reaction to the right, okay, in an attempt to equalize the concentrations. Questions? Good job today, guys. We worked hard. All right.